This is where we stopped in the last module. We have worked out an expression for uncertainty in position, and that turns out to be L square by 3 minus L square by 2n square pi square. Well, to be very honest, we have not worked out the uncertainty in position yet. What we have worked out is the average value of x square, which is the first in the linear combination under square root sign in the expression for uncertainty in position. The saving grace is that we already know the average value of x from a previous module, that is L by 2. Now let us work out the expression under the square root sign, average value of x square minus square of the average value of x. This is what we need. We work it out and then put it under square root sign. The final answer that we get is L multiplied by square root of 1 by 12 minus 1 by 2n square pi square. I strongly recommend that all those who are taking this course should work this out by themselves, because it is impossible to understand it completely or be convinced just by listening to me and seeing me work this out, especially as we are not writing on a board. We are using electronic medium. Please work out this expression by yourself, then only I think you are going to be convinced. Okay. So, crux of the matter is we have this expression for uncertainty in position that we had looked for. Now let us seek the expression for uncertainty in linear momentum, and that is going to be much easier than uncertainty in position. Okay. This is the expression that we have got, and now uncertainty in momentum, what is it? Okay. Let us see. Well, we already know that out of these two terms under square root that we need to find for uncertainty in momentum, we already know that average value of Px is actually equal to 0, right. So, then this expression becomes a little simple. It turns out to be square root of average value of Px square. Please do not think that the square root of average value of Px square, the square root and square will take care of each other and it will turn out to be average value of Px, it will not. Remember the task I gave you in the last module, take a set of numbers, work out the average of squares and then work out the average of the numbers themselves, take square, you will see they are not the same. So, it has to be written as square root of average value of Px square. It is a root mean square quantity analogous to what we have studied when we talked about say speeds of gas molecules in kinetic theory. There we talked about root mean square velocity, is not it. So, this also is a root mean square expression. Do not think that the square and the square root will take care of each other, they will not. But the good thing is all we need to do is we need to find this average value of Px square. How do we do it? Like this. We know already how to find the expectation value. So, we write the wave function, and in this case we are working with a real wave function. So, it is so psi star equal to psi, the wave function multiplied by Px square operating on root over 2 by L sin n pi x by L. Take this, integrate between 0 to L and you are home. Well, almost, because you still have to take a square root. So, what is Px that we know, h cross by I ddx? What is the operator for Px square? That would be making the same operator operate twice, that is the meaning of operator Px square. So, make it operate twice, what do you get? H cross by I multiplied by h cross by I, that gives us minus h cross square, and then ddx operated twice gives us d2 dx2. So, this might ring a bell actually, because when we talked about Schrodinger equation we got something very similar to this. Remember the Hamiltonian operator, the first term, the kinetic energy operator, was minus h cross square by 2m. Why? Because kinetic energy is Px square by 2m. Okay. So, all our discussion is in sync. So, Px square operator is minus h cross square d2 dx2. Now, now what we have to do is we have to take this expression for the operator, plug it in the expression for the plug it into the integral. Let us do that. This is what we have, minus h cross square comes out of the integral sign, d2 dx2 of root over 2 by L sin n pi x by L. I am intentionally not taking this root 2 by L and root 2 by L out, because if I can keep the wave functions, then I know what the integral is when the limits are 0 to L. The integral for psi x square is equal to 1. Now, and also the good thing is here we have a sine function. So, what happens when I take second derivative of sine? I get back the same sine function. The only thing here is that you have to take care of n pi by L. For every differentiation, this n pi by L will come and we can take it outside the bracket. So, this is what we get: n square pi square h cross square divided by L square integral 0 to L root over 2 by L sin n pi x by L multiplied by root over 2 by L sin n pi x by L dx. Now, what just happened? Where did I get n square and pi square and L square? Well, because remember we differentiated twice. So, first derivative of sin kx is equal to k multiplied by minus k multiplied by cos kx, right. That is why the minus sign also came out in the first differentiation, and that took care of the minus sign that was already there. And then when you differentiate the cos kx function, again 1 k comes out. That is why you get k square outside and you get back your sin kx. So far so good. What about this integral? As we said a few seconds earlier, this integral is equal to 1 because we are working with a normalized particle in a box wave function. This is equal to 1. So, the expression for the mean of square of linear momentum turns out to be n square pi square h cross square divided by L square. What is sigma px? Sigma px is just the square root of this. Let us find it out. It comes out to be a very simple expression n pi h cross by L. So, earlier we have determined the uncertainty in position, now we have determined uncertainty in momentum. The next task is to multiply them together, multiply them with each other and see whether uncertainty principle is satisfied by this system of particle in a box that we are talking about. Sigma x, remember, is L by 2 n pi square root of n square pi square by 3 minus 2. Sigma px is equal to n pi h cross by L. Let us multiply them. This is what we get. What happens here? L and L cancel each other, n pi and n pi cancel each other. So, you are left with h cross by 2 outside the square root sign. Inside the square root sign you have n square pi square by 3 minus 2. This is what you get. Let us try to see whether we can get a simpler expression here. What is the value of this n square pi square by 3 for the smallest value of n? What is the smallest value of n? Smallest value of n is 1. We are talking about particle in a box. So, if the smallest value of n is 1, then what is the value that we expect here? Pi square, pi is 3.142 in fact. So, square root of that is going to be, well, square of that is going to be more than 9, okay. You do not need to remember the exact value. So, more than 9 divided by 3, what is that? That is more than 3. So, more than 3 minus 2 is more than 1. So, what you have under the square root is a real number which is more than 1. Does not that prove that for any value of n, this product is always going to be greater than h cross by 2? You see in this expression h cross by 2 is multiplied by this quantity under square root, which we have shown is always more than 1. That is why the product of uncertainties of position and momentum for particle in a box turns out to be always greater than h cross by 2, which is nicely in agreement with uncertainty principle. So, we have demonstrated that uncertainty principle is obeyed for a particle in a box. Remember, non-conformity with uncertainty principle sounded the death knell of Bohr theory. So, it is comforting to know that the first system that we have studied using the wave mechanical treatment of Schrodinger conforms with uncertainty principle. So, a very major problem that was there in Bohr theory is not there, at least so far. So, the next question we want to ask is that, is this a specific case that only for particle in a box uncertainty principle is valid, or do we expect for this wave mechanical treatment that it is not going to be, it is going to be valid for everything? Is there a general way in which we can look at uncertainty principle itself? So, this discussion might sound to be a little bit of digression, because after all the topic under which we are performing the discussion is particle in a box, but this digression, if I can call it digression, is definitely worth it. So, bear with me. So, let us see, let us understand uncertainty principle a little bit better. To do that, let us revise what kind of wave functions we have for your Px. So, Px again we know is h cross I by I ddx, and a good wave function for this is psi equal to e to the power plus minus ikx. The wave function is an imaginary wave function, but it is important to note that the eigenvalue is not imaginary. Eigenvalue is definitely real, because when you differentiate e to the power plus minus ikx with respect to x, you are going to get plus minus ik multiplied by the same function. So, that I and this I are going to cancel each other. So, Px operating on psi gives you plus minus kh cross e to the power plus minus ikx. We have touched upon this in one of the previous modules, but let us make sure that once again everybody is on the same page with this. So, this as you see is an eigenvalue equation with e to the power plus minus ikx as the eigen function. Is it normalized? We have not tried to normalize yet. May be normalized, may not be normalized, let us not worry at the moment. What is more important is that it is an eigen function of the linear momentum operator, and the eigenvalue is a real eigenvalue kh cross. Well, the way we have written it plus minus kh cross. What does it mean? It means that the linear momentum associated with the system, associated with this wave function is plus minus kh cross. That plus minus kh cross is the value of the linear momentum. No surprise, root over 2 me divided by h cross, right, that would better be the linear momentum. Now see, what does this plus or minus sign signify? Kh cross is a magnitude, we understand, fine. Plus means that direction of motion is along positive x, and minus means the direction of motion is along negative x. So, sign of the wave function specifies the direction of the motion of the particle. Remember, we are right now talking about one dimensional space, right. So, if it is just plus minus ikx, then direction of motion. If it is plus ikx, then your momentum is defined very well. If it is minus ikx, then you know you have 0 uncertainty in momentum. Okay. Let us say I am not saying plus minus, let me say it is plus ikx. Then what is the value of linear momentum? Plus kh cross, one value, no deviation. This is not average value. Every time you do the experiment, you are going to get this eigenvalue kh cross, right. So, for this wave function e to the power ikx, no matter whether the sign is plus or minus, momentum is defined very nicely, is defined precisely. What about position? Position x can take up any value, right, because you work out the expectation value of position also here. What will it be? Position is x multiplied by the wave function. X hat operator is just x multiplied by wave function. What do you get? You get x, x is a variable. So, the uncertainty in position is infinite, it is defined by the boundaries. So, what we see here is that the moment the momentum is specified precisely in the wave function, position becomes infinitely uncertain. This is the philosophy of uncertainty principle. But let us go ahead, and before we make that statement, let us see what happens if we can get a situation where position is better defined. What happens to your momentum then? To do that, let us take this wave function. We are very familiar with this wave function, cos kx, sin kx, sort of particle in a box like wave function, that as we know can be written as a linear combination of exponential imaginary terms. Okay. Let us say we have chosen A and B in such a way that we get either cos kx or sin kx. Actually in the diagrams that we are going to show you, we are going to use cos kx, it is a little more convenient. But let us not forget, cos kx and sin kx are basically same. The only difference is a phase shift, right, where cos kx is equal to 0, sin kx equal to 1, but the shape is the same. So you just have to give an offset to x, then sin can become cos. Okay. So let us say we work with this wave function. If this is a wave function, then what does it mean? It means that your linear momentum can be either ik or minus ik. So there is a little bit of uncertainty in linear momentum. Two values are there, px can be plus kh cross or minus kh, sorry I said ik, that was a mistake, plus kh cross or minus kh cross. What about position? Position, we can understand position by looking at the probability. Probability is mod of psi x square. So if you plot this function mod of psi x square, here it is just psi x square, what do we get? We get some regions of greater probability density, some regions of 0 probability density, some points at 0 probability density. So if you just take a small slice dx, then in this position and this position and this and wherever there is a maximum in this plot of psi square, you get maximum probability of occurrence. So that is the position. So what we see is that position gets a little better defined. At least we can say that the particle is more probable to be here, here, here and here and less probable to be here. Earlier position could have been anything, all values of x had the same probability when you took one of the exponential terms. So we have demonstrated that if we introduce a little bit of uncertainty in momentum, position becomes more precisely defined. Let us now go way further. Let us take a large number of e to the power ikx and e to the power minus ikx for different values of k, and let us add them up like this. Let us now work with sum over j, aj e to the power ikjx plus bj e to the power minus ikjx. Coefficients aj and bj are chosen in such a way that you get say cj cos kjx, okay, that kind of a wave function. So right now we are just making up wave functions, so everything is in our hands. What happens then? What happens to momentum now? There are many values of j, right. I have not said how many values of j are there. Maybe there are 1 lakh values of j. In the expression that I am going to show you, I have taken a combination of about 10 values of j. So momentum has become more uncertain depending on how many values of j we are working with. You can have k1, k2, so what is momentum? Kh cross. So you can have plus minus k1 h cross, k2 plus minus k2 h cross, so on and so forth, depending on how many terms we have taken. So when we take this linear combination, we get this kind of a wave function where your position, your momentum has become significantly more uncertain. What about position? To get position, once again we are going to take a square of this sum. It is easier if you take a square of this sum over j cj cos kj square. When we do that, we get a plot like this. Now see what has happened. Now the other positions, here there is a local maximum of probability density, but it is so small. Same here, the clear global maximum of mod psi square appears at this position of x, where all the cosine functions are in step. For x equal to 0, for all cosine functions the value is 1, the maximal value. That is why here all these cosine waves are in step. As you go further, what happens is there is a phase difference between all, right. So, the waves start getting out of phase. This is a phenomenon that is made use of in things like Fourier transform, time domain spectroscopy as well. You have waves of different frequency, at one point they are all in step, then they start getting out of step, you get destructive interference. So, what you get finally is that your linear momentum in this case is highly uncertain, as we have said, position gets reasonably well defined. And for the records, this kind of a situation where we have taken a large number of waves that are in step at a particular point, this is called a wave packet. And one can even experimentally generate wave packets, and wave packet dynamics is something that has been of interest to physical chemists, spectroscopists, quantum chemists for several decades now. And then they provide very important information about how things proceed in ultra short time scale in systems. We have discussed this in more detail in the NPTEL course on ultra fast spectroscopy in chemistry that was offered last semester. Whoever is more interested can have a look at those lectures. But for now what we have got is that the moment we made linear momentum uncertain, we generated a wave packet which had significantly better, significantly more precise information about location of the particle. So, what we have shown here is that in uncertainty principle, if linear momentum is well defined, position becomes ill defined automatically. In situations where position is better defined, linear momentum becomes ill defined automatically. So, the wave mechanical treatment here of Schrodinger is absolutely in line with uncertainty principle, and using it we also get to realize that uncertainty principle is really the threshold of nature beyond which we cannot go. Here let me acknowledge my teacher Professor Rupendranath Banerjee of Jadavpur University, who actually taught me this expression threshold of nature when I was in class 11. It is because of great teachers like them that students like me learn certain things that we perhaps would have not understood so well otherwise. Right. So, it is not possible to make a better instrument. If we think that we will make a better instrument and will determine linear momentum and position correctly, it is just not going to happen. It is not about instruments, it is an inbuilt law of nature that in microscopic world, if position is well defined, momentum cannot be, and vice versa. And it is not restricted to just position and momentum also, it is a feature that you see for all conjugate properties, energy and time for example. Now, since we are talking about uncertainty, let us talk a little more about the workings of quantum mechanics, and let us make this statement: when operators do not commute, properties cannot be determined simultaneously. What is that supposed to mean? Commutation means you have two operators, let us say x and px. You make px operate first on a wave function, you get whatever you get, another function, make x operate on it, you get some value. Then invert the sequence of operation. If you get the same quantity, then x hat dot px hat minus px hat dot x hat would be equal to 0, which means the commutator is equal to 0. We will see it right now. Okay. So, these are the wave functions we are working with. Let us do x hat px hat psi, which means when you write like this, px hat operates on psi first, then x hat operates on it. So, x hat px hat on psi, what is it? It is x multiplied by h cross by I d psi dx. Now, we are not using particle in a box wave function, it is a general statement. x multiplied by h cross by I d psi dx. Let us do the commutation. Let us invert the sequence of operation Px hat x hat psi. What would that be? X hat operating on psi is just x multiplied by psi. So, now you have to make this h cross by I d dx operate on the product of x and psi. We all know what d dx of uv is. It is this Px hat x hat psi gives us h cross by I x d psi dx plus psi. Very simple, I am not going through the step. So, now what is Px hat x hat psi minus x hat Px hat psi? It is not 0, it is h cross by I psi, and we can write it as an eigenvalue equation. We can write it like Px hat x hat minus x hat Px hat psi is equal to h cross by I psi, and in fact this operator is often written like this, that x hat comma Px hat in third bracket, that means the commutator of x hat and Px hat, that is equal to IH cross. So, what we see is that it is not equal to 0, and then a postulate of quantum mechanics is that when operators do not commute, properties cannot be determined simultaneously. We will have some examples of operators that do commute in the assignment. Right. So, this is what we have discussed so far. We have considered a very simple model of particle in a box. We started with particle in a one dimensional box, and then we extended it to 2 dimensions and 3 dimensions, and then from this very simple model we have learned so many things over the last 4 modules I think. We have even learned how we can see that wave mechanical treatment in general is in keeping with uncertainty principle. So, sometimes students complain that whenever we try to study quantum mechanics or quantum chemistry, this particle in a box model keeps coming back and is taught many times. There is good reason for it. In fact, even in this course we are going to refer to the particle in a box model once again when we talk about say variation principle. Okay. This provides a good testing ground for sophisticated treatments as we had said. But for now we are done with that discussion of particle in a box, where the particle is confined within a box where the walls are infinitely high. Potential energy outside is V equal to infinity. Let us now move on to a variant, and let us now finally tackle the question, what happens if the potential barrier is not infinite? What happens if the potential barrier is finite? When I put it like this, perhaps it sounds like a question that has arisen out of just curiosity from doing so much of theory. That is not completely true. In fact, this question arose out of an experiment. In the very early days of quantum mechanics, early 20th century, it was found that people worked out the and I am not taking the name of the people, you work out itself, it involves people like Gamow and Rutherford and other stalwarts. The kinetic energy of alpha particle emanated from a radioactive nucleus was worked out, and the potential barrier immediately outside the nucleus was also worked out, and it turned out that first of all this potential is finite, and it turned out that the energy, kinetic energy of the alpha particle is actually lower than this potential barrier. So, now the question came, how does this come out? It appears that when the potential barrier is finite, the particle can somehow come out of that, overcome the barrier, even though its energy is less than the energy associated with the barrier. How does that happen? The question of finite potential energy barrier arose from here, and that is what we will discuss in the next module.